Hello and welcome. This is Module 8, Segmentation for the Netplus guide. This is one of those chapters that you really want to learn for networking because everything runs on VLANs or virtual LANs. And also you need to know how to calculate subnets, how to subnet your networks, and how the whole mechanics is seen from the network side, from the routers and from the switches themselves and from the clients. So imagine trying to control a network with 2,000 users and all the users on the same LAN. So it'll be quite difficult to segment those devices, those networks, clients who belongs to one department to another. So segmentation, it helps you to separate that, break the network in pieces, kind of like break it up in smaller pieces that are easier to control. That helps you to prioritize your network, to direct your traffic to different places that you want to. And also to filter if you want to filter some devices not to be able to do certain things. So now you start separating things within your network. So you enhance security, you improve performance, and you simplify troubleshooting because now you got things separated. You can separate by geographical locations. I mean, it doesn't have to be in a town or a city, but geographic location meaning a building having multiple buildings, so each building is separate, seen separate, or even each floor, or even within a floor, you can have the floor split up in 4 areas, and each area is handled with like a different LAN. So you can do departments, you can do by devices types. For years, I've been trying to get at the college to have all the printers in per campus separated on a separate network, so you can now you can control who can get into the printers and who cannot, and where the printers can go to. So that's when you start to really take control and manage your network. So all group of computers working on a LAN, on a local area network, is called a broadcast domain. A broadcast domain is an area where when you do a broadcast, who's going to be listening on that broadcast? Which computers are part of your network? That's called a broadcast domain. And if you have a classful IP address, it's a large broadcast domain. Imagine Miami-Dade College, we own the 147.70.0.0, and that is 65,000 IP addresses. So you cannot possibly have a 65,000 client broadcast domain. So you can break it up into smaller domains, smaller subnets, so kind of smaller subsets of your IP address, and then you create a LAN 1, a LAN 2, or a VLAN 1 or VLAN 2. We'll get more into what a VLAN, a virtual LAN is, so you can understand the concepts. But it's basically separating things into, now every time I break that up, I create a new broadcast domain, and that's the broadcast domain for my clients within that LAN. We have been talking about binaries. Remember that we did an assignment on binaries, so you could learn some of the ones and zeros. How do they see how they're seen from the network side, and also that brings back into ties into what it is a subnet mask. I also mentioned that before when I said, remember that if you have a block of 142nd Street, so it includes all the houses from 142.00 to 142.99. So if I mask for the first 3 digits on that address, that means that everything that starts with 142 is part of my network or part of my block. It goes from 00 to 99. And we can call it actually on networks on an IP block. That's your block. So, but if I move my mask to 1420, that means that I'm only including the houses that starts with 01 all the way to 09. Because when I go to 142.10, that digit there doesn't match. I'm looking for a mask. That mask means that if it matches this, you're part of my network. And that will make it into a much smaller set of homes that goes only from 142.00 to 142.09, because 142.10 then belongs to another set. But what if I do move that mask to the left? And I said, well, I'm going to mask only 2 digits, the 14. And 14, that means that now I'm including 140th, 141st, 142nd, 143rd, 144th, 145th, and all the way to 149th, right? Because I'm masking only to match those two. So now I'm looking at things from a broader area. You see what where I'm going to? You can start by looking at something really small, and then something larger, and then larger until you start collecting everything. So that makes segmentation much easier when you start dividing things and just seeing things from a perspective on only a small subset. So now let's see how subnet mask can help you. With subnet mask helps to break a network into multiple pieces, right? So if I have given a 192.168.1.0/24, /24 remembers the 24 bits for a subnet mask. That means that my mask is 255.255.255.0, which means that the first 3 octets of my IP address needs to match in order to be within my network, be part of my network. So that anything that it has 192.168.1. anything is part of this network. So I can take this and break it apart into 3 sections and allocate a range of IPs on the first floor, a range of IP on the second floor, and another range on the third floor. So that way, when I connect to the switches and go back to my router, then my router now can segment this and allocate traffic that goes to the second floor, to the first floor, and to the third floor, separate. And each of one of these, it's a broadcast domain on its own. So now subnet 1 is a broadcast domain, subnet 2 is another broadcast domain, and subnet 3 is another broadcast domain. All right, so how is that done? Well, the subnet mask is a set of ones in a string followed by zeros. The ones indicate the network part, and the zeros indicate the host part. So it's 2 pieces, the network and the host, right? And what the network mask would do, or the subnet mask would do, is that these are the ones that I want to keep. So anything that's underneath that that matches that string of ones and zeros is the one that has to be on my network. So let's explain this a little bit better. You got the IP address 192.168.123.132. In binary, that is what it shows there: 1100.000.101.001.000. 0111 and 132 is 100.0.100. So my subnet mask being 255.25.25.0. Remember, 255 is the highest number you can have on any IP address, right? This is all IPv4, right? So 255 means a whole string of zeros, 8 zeros. 1111, 1111 dot 1111, 1111 dot 1111, 1111 dot 0000. So when the network sees this pattern, it compares the IP address with the subnet mask and says, okay, so what I'm looking for here is to match those first 3 octets, the 192, the 168, the 123. If they match that pattern of ones and zeros that you see on the top, if it matches that pattern, that means that you're part of my network. You're part of my network ID. My network ID is 192.168.123.0. On the subnet mask, I call my zeros, I call them my don't cares. I don't care what they are, because whatever it is still going to be part of my network. So if I match those, that means that the host portion is 0.0.0.132, because your network is already know that where is 192.168.123.0. And from that, you have a unique address assigned to you, which is the 132. So now anybody on the network that matches the 192.168.123. something, it will be part of my network, my broadcast domain. Why? Because my subnet mask is telling me that. And literally, the routers and the switches, remember that they know numbers, but when they goes into their computing, everything is binary. So they will look at those binary numbers and compare the binary numbers. That's why I insisted so much on the assignment on binary, so you start getting to see what these actually are. So we said that that subnet mask is a string of ones, right? It's a string of ones followed by zeros. So if I have that /24, which is 255, the 255, 255, the 0, it's a whole set. The three first sets is just ones, and then the last octet, the last 8 is zeros. If I start moving that subnet mask to the right, adding more ones at the beginning, so that is it's not only 24 bits, right? Then I add 25, 26, and I keep on going like that. That is going to increase my number of networks, but then it's going to reduce the amount of bits that I have for my host. So by doing that, I reduce the number of hosts, because now if I take the first bit, I said if the first bit of the last octet is part of my subnet mask, that means I cannot touch it. It's going to be either 0 or it's going to be 1. So by doing that, I'm taking the bit that is 128, right? Remember when it goes, when you double the numbers, 1, 2, 4, 8, 16, 32, 64, and 128, the last bit is 128. So if I include that into my subnet mask, and that bit is a 0, it means that all the numbers can start from 0, 0, 0, 0, 0, 0, all the way to 0, 1, 1, 1, 1, 1, 1, 1, which happens to be 127, because the next one is 128, but the bit 128, I cannot touch it. If I touch it, it changes into a 1. So now I go from 128 to 129, 130, and so on. And that will take it all the way to 255. So now by taking one more bit, not 24 bits, but 25 bits, my host that used to be 255 is broken up in half, from 0 to 127 and 28 to 255. So let's do this example. I got 192.168.89.0 with a mask of 255, 255, 255.0, which is a /24. It's a 24 bits. And what I'm going to do, I need to break it into two subnets. So I'm going to borrow the first bit from the host portion. Remember that says is a .0. That means that all the last octet is all zeros on a subnet mask. But I'm going to borrow the first bit. So my mask will end up being the 1111 dot 1111 dot 1111 dot 10000000. So that means that to be part of that network, those numbers there will have to match. So my subnet mask now is going to be a /25, because now I have 25 bits, right? So my mask is 255, 255, 255.128, because that's the bit 128, right? The first one. And I'm going to break it into two networks. So to me, imagine having a page that it goes from numbers from 0 to 255, and you fold it in half. If you fold that in half, exactly, you're going to have 0 through 127 on one side and 128 to 255 on the other side. Now, that means that I got two networks. The 192.168.89.0, which is the first IP of that one half. And if I go to the other side, the first one's going to be 192.168.89.128. Both of them is /25. So the first IP address on your range is your network number or your network ID. That number cannot be used on a network. It is your network ID, and it cannot be used for a router or a client or anybody else. The same thing happens with the last IP address, which is the broadcast, but we'll get into that a little later. So what happens now is that I got two ranges, right? Because now I broke that into half. So I got the 192.168.89.0/25, and my range is going to be 192.168.89.1. That's my first usable IP address, to 192.168.89.127. And remember, this 127 is the last one that I cannot allocate to any client. That's the broadcast IP address. So on the next range is the 192.168.89.128/25 with a range that goes from .129 to .255. So when I present this to a network and I said, hey, this is my network is /25, all the routers and all the switches are gonna understand that these are two separate networks. That whoever has an IP 175 is not on the same network as 89.50. Because 89.50 is on the first range and 89.175 on the second range. And when we did that subnet masking, then we split the network in two completely independent networks. Now, what do you need to communicate from one LAN to another LAN? You need a router. The routers are the only devices that can actually talk to two VLANs and transfer network traffic from one VLAN to another, from one LAN to another, right? So now for these two ranges, for them to be able to talk to each other, you have to go through a router. Switches themselves are layer 2, and they don't know that there's a gateway, 89.1 and 89.129. So there's two separate LANs, completely separate LANs. And the only way they can talk to each other is through a router. Now, this is an example that I'll have to work it in class so I can be more interactive. Um, because right now my screen is fixed. I cannot add while I'm talking. But anyway, so this is kind of like a tricky question because it says that you have a 192.168.89.0 and to divide it into 6 subnets. Now, I'm saying it's a tricky question because remember that we're talking about binary. Binary goes everything by sets of 2s, right? So when I have a subnet that is /24, that's one single network, right? I can break that network into two pieces. So if I do /25, like the previous example, then I get 2 subnets. Now, those 2 subnets can be broken even further, each one of them into 2 pieces. When I do /26, now I'm borrowing another bit from from your network, less hosts, but now it's broken into 4 subnets when I do /26. So now before we had sets of 128 plus 128. So now when I break it into halves, I get 64. So I got 64 plus 64 plus 64 plus 64. That gives me a 4 sets of 64 for a total of 255 or 256, if I include the 0. And then those 4 can be broken again, each one of them by half. We can only do halves. This is binary. In binary, you can only do, ones and zeros. So it's either the whole or the half. There's no other number. Remember, that's the whole thing is a base 2. So everything can do only halves. So now those 4 pieces that I have, those 4 subnets, I can break each one of them in another half. So that will be moving the mask one bit more. So it goes to /27. Now that gives us 8 subnets. So yeah, he's asking you for 6 here. So you're going to have 6 and 2 that you're not going to be using. So /27 gives me a mask of a series of 1s. And you see at the end, you got 1, 1, 1, 0, 0, 0, 0, 0. Right? Because that was like we had 24 for the first 3 octets, and then the bit 25, the 26, and the 27. So that's the first 3 bits. So that means that when I do my network, I cannot touch those. Those are part of my network. And we'll work out but the network IDs for each subnet and the range in class. So now you end up with 8 subnets. So the thing what you have to look into here is that the only portion left for hosts is on the last octet that I'm allowing me to do 0, 0, 0, 0, 0. It's only 5 more bits, right? So that means that if I go 0, 0, 0, 0, that's a 0. And it can go all the way to 1, 1, 1, 1, 1, which happens to be 31. So my first subnet will go from 0 to 31. Now, that's assuming that the first three bits, those 3 X's, are zeros. But on the network, on your network, then that of course can change, can be anything from a 0 and a 1. So when I change the first bit to a 1, now my range doesn't start on 0. I got 0, 0, 1, 0, 0, 0, 0, which that's at 32. So my range there starts from 32 and it goes all the way to 63, which is the next set of 32s. And then based on that, you'll do, okay, which is your network ID for each subnet is the first IP of that. The broadcast is the last one of that range. So it would take the example of the first one, the network will be the 192.168.89.0, and my broadcast is 192.168.89.31. Like I said, if you keep in mind that if you have a piece of paper with all the numbers and you fold it in half and you fold it in half again, that's how networks can work in binary. That's the only way to group them in different sets, but they have to be binary sets, right? Which is the smallest one I can have? 2, right? I can do 1 by itself, and then I can do 2, then I can do group 4, I can group A by P's, and then 16 and 32, 64, 128, and keep going like that. So any network can be subnetted. If it's a class A, a class B, or a class C, they can be subnetted. Remember that the class 8 are all those networks that starts with a 0, and they go up to the 127. The class Bs are the one from 128 and higher. Miami-Dade is a class B at 147.70 because it's higher than 128, right? But any of those networks can be subnetted. Anything, any network, even the private networks, the 10 dot something networks, the 192.168, the 172.16s, all those networks that are even private can be subnetted. And each one of them depends on that subnet mask to determine which is the network portion and which is the host portion. Remember, the network portion is the one that has to remain the same to be part of a LAN, and the host portion is just a unique IP that you get. Right? So that network will depend on how you're going to subnet your network. And there are many ways to do it, many ways to slice it. And there's an example for that we're moving forward that it will show you that. Also, there is a subnet mask table that is on page 437 of the book that shows you everything on a class B subnetting with all the subnet mask. That will show you how many hosts and how many networks you're going to have per each subnet mask. So for the exam, yes, there will be a valid question to say you have this network and this is your network mask. Then tell me which is your network ID, your broadcast, and your first and last host IP address. That's because you're going to be seeing this almost every day in your IT world. When you work in IT, you're going to be seeing this every single day. For the most part, networks are subnetted with a /24 with a 255.255.0. But there will be even larger networks. At the college, we use some of them that are /23, which they're not 255 IP addresses, but now we be borrowing one from the host portion to give more, more from the network portion to give more hosts. So by doing /23, which is moving to the left, not to the right, then my hosts, rather than being 255, they double up, and I get 512 clients. And like if I'm moving forward, like we do on the wireless, your subnet mask changes because it's a /22, and what it gives you is double that. So that it's not 512, but it's also 1,000 because we want that. We want all the wireless clients to be on one big LAN. We expect to have at least 1,000 clients or no more than 1,000 clients. So that's why we assign that. Remember, 255. If I move one bit, borrow from the network portion to give more hosts, then we'll double it, right? Like the same way we divide it, if we move to the right, we double it if we move to the left. So when it's a /23 rather than 24, we're moving to the left, right? Your host portion is no longer 255, it's double that. It's 512. And then if I move one more bit, the /22, then that gives me 1,024 IP addresses, and we can move it again. I get 2,048. That's with the other clients. But for the most part, like large networks like that, like for the Wi-Fi, we allocate that because we know for sure that we're going to have more than 255 clients. So we need to have a broadcast domain and a whole bunch of IPs that are together on one single LAN, and they can all talk to each other and be all in the same network. We don't want to separate those. Yes, I want to separate open and student, and I want to separate also the secure wireless. So all those three will have on its own a set of IPs for 1,000 on one, 1,000 on the other, 1,000 on the other one. So now I can support 3,000 clients on my Wi-Fi. So following the thought of that network that we had before, the 192.168.89.0, we broke it up with the /27. And the /27 is the one that gave us like 8 subnets. So the first one here is 89.0 on switch C. And the second one, the network is 192.168.89.32/27. And the last one, it's the 192.168.89.64 /27. And as you see here, they're jumping by sets of 32. Why 32? Because 32 is a whole binary number. The 1, 2, 4, 8, 16, 32. You cannot bring a network any random number, say 20. You can't. It has to be part of a binary group. You know, kind of like when you are counting in tens, in decimal, and you go 10, 20, 30, 40, 50, 60, 70, 80, 90, you can't have 25, you can have 75 because you're counting in tens. So you can't just say, oh, I have 17, number 17, because you're counting in tens. So it just doesn't apply because you're counting in groups of 10. So here is binaries and grouping, I'm going in groups of twos. So it has to be like, you know, the 2, 4, 8, 16, 32, like that. And then I can go with the next group. Right. So if you see to the left, the first IP address of that range, the subnet is 89.0. So the first one is 89.1. That will be my gateway. That's the gateway IP address. So the switch will connect to the router on that gateway, which is physically configured on that interface. It's manually configured. It says, hey, for this link to switch C, this is the IP address for that segment. And then for switch B, that segment, which the network number is 89.32, the first IP address is 89.33. So see the convention. We're using the first IP address for the gateway. And the last one is 89.64, the network number. So the first IP address is 89.65. And that's what is going to be configured at the router. Those numbers are configured at the router. So now, if I have a computer on the third floor and the IP address is 192.168.89.70, it's part of that range. It's on the third floor, but he needs to talk to a computer in 89.10, which is on the first floor. Well, 89.10 is not part of the 89.64 network, right? Because it's 64 to 96. So, yeah, 32 plus 64 is 96. So it will go from 64 to 96. So if it's anything within that range, yeah, that's part of my LAN. But if it's not on that range, then it's in a different LAN. So what do I need to do? I need to go to my gateway. My gateway is 89.95, 65, I'm sorry. Go to the router and said, hey, I'm trying to communicate with 89.10. Do you know where that is? And the router says, sure, I have a network here. The network 192.168.89.0/27. That range goes from 0 through 31, and 10 is part of that one. So I'm going to send this to switch 10, I'm sorry, to switch C. Switch C, it has that computer in there because it belongs there. It's not going to send it to switch B because switch B, it's the range that goes from 33 to 63. Because 64 is the next one, right? It's the one on the third floor. So if it will not send it there. So the router knows it's going to take that IP address, it's going to apply that mask, and based on that mask, he will know from that 192.168.89 if it belongs to the network that is on switch A, B, or C, based on that subnet mask. And the subnet mask is going to tell him the range of the hosts in that specific network. So as you see here, you need a router and you need a gateway configured at the router. Who gets IP addresses? The router, not the switch. So you're not going to say, oh, the gateway is configured at the switch. No, the switch are layer 2 devices. All they know is MAC addresses, and they forward traffic to the router. If anything is within the same LAN, yes. But if not, it will forward to its own gateway at the router, and then the router will make the decision. Does it go to the first, to the second, or to the third floor? Now this is more expanded way because now you have the 6 networks that they wanted. So you got the 89.0, the 89.32, the 89.64, 89.96, 89.128, and the 89.160, right? I don't like this slide because it shows you the network but not the router, the gateway for each of those networks. It doesn't tell me those gateways. But let's assume that it's going to be the first IP address of every network. The numbers there are the network numbers, not the gateway numbers. But anyway, so on top you have a switch with 2 devices. Then you got another switch with 3 devices, includes a printer. Another one with just 1 computer. Then the 2 computers, and the last 2 is just the 2 computers and a printer on the 160 something network. So let's say my printer on 192.168.89.172 needs to talk to the computer on 89.73, right? It's a switch there on towards the right in the middle. So he will have to go to his own to the gateway at the router. 192.168.89.161 will be that. That router will get that traffic, will send it to the gateway for that other network, for the 64 network, which the IP of the router should be 89.65. That's why I say this. It's incomplete because it doesn't have those IP addresses there. But the 65 then will send it to 73 because, yeah, this is my network. And the router doesn't need to flood all the networks. Says, hey, where is this computer? No, he doesn't have to. The router knows all by having the gateway configured there. You also have the network mask. So by having that, the router knows exactly the range for each interface that he has on each of all of those 6 networks. So he will forward the traffic on a specific port and to the LAN that it's supposed to go to. Routers are smart devices, layer 3 devices. They know everything about IP addresses, so they can handle all that. But he needs to know the IP address and he needs to know the subnet on each interface facing all those LANs in order to make those decisions. So here we can apply the concept of DHCP, the Dynamic Host Control Protocol. That's the one that assigns IP addresses to the clients. So when I turn on a client, the client doesn't have an IP address. And basically, that's a broadcast that says, hey, I need an IP address. So the router at the gateway will have what is called an IP helper. The IP helper address or the relay agent is what tells the router, hey, if any request comes from someone asking for DHCP, send it to this IP address. And that points to an IP address for your DHCP server, either a Windows machine or a dedicated DHCP server, because you can have a dedicated DHCP server. So it uses UDP. It just says like a packet out. It says, hey, I'm looking for an IP address, and it uses port 67. DHCP is port 67. The router will get that. It will use that relay IP address. I said, okay, let me forward to that. And then now he's the relay agent, the router. So he's going to relay that to the DHCP server. The DHCP server is going to send a reply back with the IP address and all the information for the subnet mask, for the gateway, and everything else, how to configure that IP address on your computer. Send it to the router, and the router will, in turn, he will return that packet back to that IP, that client that was requested an IP address, so he can configure itself with that information. Now the DHCP server keeps information on all of those assigned IP addresses, so he will not assign duplicates. He will know he has a track of everything, or sometimes he will just like try to say, hey, who has this IP address? Nobody? Okay, let me assign it to this computer that's asking for an IP address. And since the relay agent is the gateway from the router, that means that that specific gateway has a subnet mask, and that subnet mask specifies the range of IPs that DHCP pool is going to have. It's a pool of IP addresses. So if I have the 192.168.89.0/27 that goes from 0 to 31, I'll have a range of IP addresses that will probably go from 2 to 31. Actually, from 2 to 30, because the 0 is your network, 1 is your gateway. So it'll go from that 2 to that 30, because 31 is your broadcast. Broadcast IP address that is never used. So it will pick one of those at random. It doesn't have to be in sequence. Some DHCPs are doing in sequence, some other ones will just do at random, and it'll assign one of those IP addresses from the pool. Now, VLSM is another concept when it comes to subnetting. The VLSM is a variable length subnet mask, which means it's a variable length. Remember how we took that other subnet and said we're going to divide it into we need six networks, but we can only divide it. We actually divide it into 8, because if you can divide it half and then another half, so it goes to 4, into 2, into 4, and then into 8. Well, a VLSM allows you to break those rules a little bit, and I'll show you how. So what VLSM allows me to do is to be a little bit more efficient. I don't have to break a subnet into equal pieces. It doesn't have to. So if I have a /24, which is 255 IP addresses, I can divide that in half, right? So I'm going to allocate half of those to cells, and the other half to the left, it's IP addresses that I'm going to allocate to other things. And I'm going to say, you know what? Let me take the other half on the left and break it into half again, right? So now I have the top portion with the HR, IT, and executive, and then the bottom part, which is accounting. So if you see this, sales will have probably 128 IP addresses. And on the left, there's 120 IP addresses. But I'm going to break that on 128 on the left and break it into 64. So I'll allocate those 64 IP addresses to accounting without changing that other half, because that other half I can leave it like that. It goes from 0 to 128, 127, and I'm not going to touch that one. So the other half, I'm going to break it into another half, right? So now I have accounting that has 64 IP addresses, and the other 64, I said, you know what? I have this department that's so small, I want to break this in half. So those 64 that I have on the left, on the top left, I can break it into halves. I got 32 for HR and 32 that I can still break those into another half again. And those will be 16 and 16. So if I add them together, the 16 for executives, the 16 for IT, that's 32, right? And then HR was 32, that's 64, plus accounting has 64, that's 128, plus the 128 for sales, it's a 255. So this way I have one subnet, the 192, 168, that 89, that's 0, and I actually allocate IP addresses for 5 different departments in 5 different sets of IPs. And remember, all of this has to be binary. I cannot say that I'm going to allocate the first 20 for this and the next 40 for that and the next 15 for that. No, it has to be in halves, because that's how binary works, right? Like I said, with decimal, you can only break into ones. If you're working into tens, you can only break into 10, 20, 30, 40, 50, like that. So here, you can only break it into halves. And that's why even I can have that IT and say, you know what, IT doesn't need 16 IP addresses. You know, they have only like 2 people, because 2 people can handle the whole business, right? The whole enterprise. So I'm going to take that IT, I'm going to break it in half, and those 16, so I'm going to allocate 8 and 8. And then I can allocate those for, let's say, IT servers. So now I have a separation now where I have IT clients and the servers for IT on another set of 8. But this way, when I have this separation like that, remember, these are IP ranges. So when I set up rules on a firewall or rules to allow networks and things like that, so now I have IP ranges that I can really work with. And I can say, hey, from this IP to this IP is sales. So they're allowed to do this and access these servers. But accounting is from this range to this range, and they only allowed to do certain things and get into this printer. But sales can print on their own printer, but accounting has to print on another printer. And then I go by that range of IP addresses. But now I'm separating into smaller departments. I can still control those because they're separate. So I don't want to have like the IT and executives together. So executives going to have their own IP addresses because they might have a lot of exceptions. They can do everything in the business. So that little set of IPs are the only ones that I can allocate rules or permissions for the things that they can do in the enterprise. Whereas IT is probably a little more, also they have to have access to everything. HR only to HR service and printers and stuff like that. Same thing with accounting, same thing for sales. So now I'm breaking things apart, separating things on your network. And like I said, VLSM is the one that allows me to take one whole network and break it up into uneven sizes as long as they are with a base 2 size. Base 2 meaning 2, 4, 8, 16, 32, 64, or 128. So now on this one, they've broken, the IT and the executive into smaller pieces to create more networks for the one network and some IPs unused. And I was showing you the subnet mask. So sales, of course, is going to be /25 because that's the one that gives you 128 IP addresses. Accounting is /26, which is half of what a 25 would have, so it's 64. And HR has a /27, which is half of what accounting would have, so 64 divided by 2 is 32, right? And then now they make it difficult for me now because now they got 29. So if HR was 32, 27, then 28 is 16. And 29 is 8. So now I got 8 IPs for IT and 8 IP for executives. And then I'm doing this /30, which gives me only like about 4 IP addresses for the one part I guess that has two one connections, the yellow and the white, and then slash 29. I think that was 8. That are unused. They could be used for something else later on. So I can still break all those apart as long, like I said, you can break it into pieces that they're halves. Then you're good. So now, how do I do this in IPv6? Well, IPv6 was made to fix a lot of problems that IPv4 has. One of those things is the way they do subnetting. So IPv6 has no classes, and IPv6 does not have a subnet mask. So you don't have to be dealing with these ones and zeros. Well, here we have to deal with the binary numbers, which will make it even more difficult. But IPv6, remember, is a set of 8 blocks, 128 bits, and I'm gonna lie, but I'm reading from a page on Google that it says that this is 18 quintillion 446 quadrillion 744 trillion 73 billion 709,551,616. That's that number of IP addresses available in IPv6. Quite a bit. So IPv6, remember, was 8 blocks of 4 hexadecimal characters, right? We say characters because remember it has numbers and letters, so it's not hex number, but it is a hex number. But it's divided into two sets. The first block, it identifies the what's called the prefix, and the last block is the interface. The interface is basically what is assigned to your IP address. Remember, that was like a hash that the computer does with its own MAC address to create that last 4 blocks. But the first block is what's called the side ID, or the side prefix. And on those 4 blocks, the last one, the 4th one, can be changed to create now your subnets. Now, those 4 hex blocks, the 4th block on the side prefix gives you also a lot of variation that you can have on your subnet. So it's a large number, but that's the one that can be changed on your prefix to identify what we call on IPv4 different subnets, and I'll show you on the next slide. So like I said, IPv6 is 128 bits, so it's divided into 2 pieces: the prefix 64 and the interface, the second half of the IP address. So if I have the prefix with the whole 64, then I have no networks, different networks. So I can make that smaller to /56 to /48, and then I'll allow the last 4 hexadecimal block to change and have a unique number per network that I want to have. And that's the way that I can now distribute those networks within my sales, my accounting, my HR, my IT, and my other departments by breaking this. But it's broken at this level. So your network prefix is the one that is actually giving up some of his own bits to give you the flexibility to do subnets. So that would be like it's a subnet ID block. So now virtual LANs. So we learned how to take a subnet and split it into multiple subnets, right? So when you split your subnet, sometimes it happens that we have employees within the same organization that are in different floors. So let's say you have accounting, but accounting is not just on the first floor. Some people also on the second floor, and some people are on the third floor. So it becomes kind of inconvenient now that since they're not on the first floor, they cannot have one of those IP addresses that were allocated on the first floor, because if they're on the second floor, they have a different set of IP addresses. So how can I actually extend that network for the first floor to the second floor, but only for those clients that are sitting on the second on the second floor that belong to the sales department per se? So that the solution for that is virtual LAN. Virtual LANs is a way to broadcast traffic into still a broadcast domain, but have the domain expand, distributed through multiple switches. Now, for this, you need, of course, managed switches. Managed switches are the only ones that you can actually create VLANs and you can actually move networks like that. But this is a way to also to isolate connections and to separate groups within different floors that belong to the same network. And you can configure temporary networks like that and reduce the cost, because now what the only way to do, let's say, have the salespeople from the first floor move to the second floor will be for me to put another switch just for the salespeople on the second floor. But if they're just like 8 clients and I got a 48 port switch or even a 24 port switch, I'm going to put a whole 24 port switch just for 8 clients. It's like it's not economical. So VLANs help you to do that. The virtual LANs. I'll show you how. So let's talk here on the two networks: the manufacturing VLAN, the green network, and the administrative VLAN, which is the yellow network. So we'll talk about the yellow and the green network. So now what I can do here is that switches are managed intelligent switches. They can carry the traffic for both networks, for the green and the yellow. So imagine having the line with the two networks in the same line, but then when you tap only with one computer, you tap only on the green one and the other one taps into the yellow one. And the same thing happens on the switch B and the switch C. So that switch C also has the green and the yellow networks. But then when you configure the switch, you have to ask the question, well, is that computer going to be on the green network or the yellow network? Because then now you can allocate that specific port where the computer is connected and the printer, say from the floor 1, on the yellow network. And it's a virtual LAN. So as per the computer themselves, even though they are on first, second, and third floor and they're connected to switch A, B, and C, as far as they're concerned for their own configuration, they're all together in one LAN. They see each other as a one LAN. The broadcast domain is just that one LAN, that yellow LAN. And all those computers that are in yellow are the ones that participate in that broadcast domain. And whenever they need to get out of that yellow network, they'll go to the router. So in this case, the router will have the green and the yellow network, and they will have a gateway for the green and a yellow for the and a gateway for the yellow. So when I need to communicate, even within the same floor, from the let's say second floor, I'm going from yellow to green. That computer in yellow has to go to the router and say, hey, I'm trying to find the green network. And I'm trying to do this computer. It goes, oh, yeah, actually came from your same switch, but it's on a different LAN. So the router will make the traffic hop from the LAN and the gateway for the yellow network to the green gateway. And then that green gateway will forward the traffic to switch B and communicate with that computer in green that yellow needs to talk to. So theoretically, virtually, they are separate networks, and each one of them has its own gateway, but they operate on the same switch. And this is all possible by creating what's called virtual LANs. So to do that, like I said, it has to be a managed switch, right? It's the only one that allows that. It can be configured through the CLI, through the command line, which is like a SSH connection through the management port, or some of them will have a web-based GUI to configure that a little bit easier. Just click, apply, you're done. So there you can create your VLANs and assign the ports to the VLANs. And then it will segregate the traffic based on the VLANs that you create. There's a concept that's called VLAN tagging. What VLAN tagging does is that it puts a little tag on the traffic. It says, this is green, this is yellow. So the green is all managed independently from the yellow traffic. And that tag, which is on the Ethernet header, is the one that identifies where that network, with that traffic, who does it belong to which VLAN. So this is more like a home network, but this is a managed switch. And you can see here they have the first port on VLAN 2, the next 2 ports, 2 and 3, on VLAN 10. Then port 4 is on marketing, and then 5 is empty, 5, 6, and 7 is VLAN 30 for sales. So when you create one of these VLANs, you can assign what's called a VLAN ID, and the VLAN ID will be that VLAN number. The VLAN IDs can go from 0, which is a 0 or which is your default, or VLAN 1, which is your default, all the way to 4095. Now, There's some of those numbers, high numbers, and there's some in the range of 1000 to 1003 that are reserved by the almighty Cisco, and nobody else can use them because Cisco implemented those way back like in the 80s, and they allocated that, and they keep using that for things that no longer needed and no longer used, but they still reserve those IP addresses. I mean, so those VLAN IDs. But the VLAN ID goes all the way from 0 all the way to 4095. And like I said, there's a few exceptions in the middle, and then the 1000, some exceptions in the higher range. But for the most part, all those VLANs are assigned. And it doesn't matter that the number is just an ID number. You can number them, VLAN 2, VLAN 3, VLAN 4, VLAN 5, VLAN 7, like that. On the network, I like to sort of match it with what the network number is, and try to, like if we have the lab 147.70.40.0/24, so that one gets the VLAN 40. It makes it simple because VLAN 40 is in the 147.70.40, and like that, at home I have the 1010.100, 1010.110, and 1010.120.0, and of course I had VLAN 100, VLAN 110, and VLAN 120 because it matches the third octet of the network. That makes it easier for me to track. But it could be any number. It just like a name. It's just like you name it, and that's the name that it has. It has nothing to do with what kind of traffic it's going to have. But it's nice to have it organized in a certain way so you can keep track of it. So this is what I was explaining, that if you have here is two networks, the blue and the pink, I guess, or red, the blue and the red network. So the switch has the separation within the switch. So one port is on blue, one port is on red, and then the connection between the switch and the router, is all tagged together, with the VLAN tagging or VLAN trunking, what Cisco calls it, to the router, because the gateways for VLAN 1 and the gateway for VLAN 2 is at the router. So the only way that those two can talk to each other is a LAN to a LAN, two separate LANs. The only way they can talk to each other is through a router. That's the only one that can route and join two LANs together. The switch, remember, is a layer 2 device. It cannot do that. Switch doesn't know IP addresses, doesn't know networks, doesn't know anything. It doesn't have any configuration for subnet mask or anything like that. All that is configured at the router. So this is the concept of the tagging that goes on the Ethernet. Like I said, is a tag, is another field on your header that identifies the 802.1q encapsulation. That's the 802.1q tag that it puts in there the number for that VLAN. So it's from 0 to 4095. It will be one of those, and identifies where that network belongs to. So if I'm on VLAN 10, it will have the tag from VLAN 10. The moment that I want to go into a destination for VLAN 20, the router will change that tag, because now he knows the destination. The destination is on another VLAN 20. So he'll remove the tag that it says that where it's coming from on 10. It still have the IP address for the source, and it will tag it with the destination VLAN number for the, VLAN 20, and they will send it to the switch. So now the switch received that traffic with a tag of VLAN 20, so he knows that traffic belongs to not network 10, but network 20. And that's how the switch now differentiates that. But the one that makes that change on the tagging for the routing is the router itself. He's the only one that can do that. And the switch will interpret that. He needs to have that in order to route correctly, then to deliver the traffic correctly. So this is another example with 3 switches. Those, I guess, like purple lines are tag links. So it has all those VLANs. In this case, switch A will have VLAN 1 and 2. Switch B has VLAN 1 and 3. And those are tagged to switch C. So of course, C to A has only VLAN 1 and 2, and C to B has VLAN 1 and 3. Whereas switch C to the router needs to have VLAN 1, 2, and 3, right? Because it's all propagating. And remember, all these gateways for VLAN 1, VLAN 2, and VLAN 3 reside at the router. He's the one that's going to make the connection between VLAN 1 to VLAN 2, VLAN 2 to VLAN 3, and 3 to 1, and all that traffic across. So when a packet comes out of VLAN 1, it will traverse switch A, switch C to the router, And then the router said, oh, you're going to VLAN 3, so let me change the tag to VLAN 3, send it to the switch C. So switch C said, oh, this is VLAN 3. It is only configured on B, so we'll send it to B. And B says, okay, I have so many ports here on VLAN 3 is one of those. Let me look at the MAC address of the origin, of the request is coming from, and then I can identify to which port I need to deliver that traffic to. And remember, all this is all known by the router because the router keeps the routing table with all the IP addresses, and also it has the ARP table, the address resolution protocol. We saw that before. The ARP is the one that ties the IP to a MAC address. So from this switch, he learns the MAC address for that computer on VLAN 3. And it keeps a table there so it knows where it is. And also when that gets an IP address, it will keep that record and say, okay, this IP address belongs to this MAC address. So now the router is aware of not only the layer 3 at the client on VLAN 3, but also the layer 2 in order to deliver it to the right switch. So this is the concept of trunking. That's trunking when you have more than one VLAN on one port. So ports can be two types. An access port, which is kind of connecting to a host. That's just a single VLAN. It's kind of like a default. Whatever you connect in there, it will go to that VLAN. Or you can have a trunk port, which the trunk port is the one that has multiple VLANs in there. So usually the trunk port are the ones connecting switch to switch or switch to router, right? Because that's where you're going to have all those trunkings with the VLAN tagging there to do that. Cisco has what's called VTP, the VLAN trunking protocol. Which is a way for them to exchange information on all those trunks. And you can, Cisco does the VLAN trunking protocol, VTP, when the switch is aware of all the VLANs that you have. I honestly don't like that. I think it's messy that the switch is aware of a ton of VLANs that doesn't belong to the switch, that it doesn't need any traffic there, but still is aware of those. It doesn't have to. If I have 50 VLANs on my network and this switch only handles traffic for 2 or 3 VLANs for 3 networks, why does it need to know about all these other 50, 47 networks if it only needs to know about those 3? So yeah, VTP is good because whenever you put a new network, you can bring it into the switch and it automatically is there. But I don't know. That's the way the Cisco does it. That's not the way that I would do it, but it is available. So you can tag all the VLANs into one switch and then use them as you need them. Now the examples are getting a little bit more complicated, right? So we have the same scenario with switch A, B, and C and the router, right? So you see the trunk lines going from the router to the switch C to A, switch C to B are all trunking. And then now the VLAN 1, VLAN 2, VLAN 1, and VLAN 3, they have the clients connected to specific ports, and those are access ports. So your clients connect to access ports. When they tell you access port, it means it has one VLAN. And normally it's called the native VLAN or the default VLAN. The default VLAN is just one VLAN that connects there, and that's it, just one VLAN, no tagging. Access port means no tag. It just whatever gets there is the network for that, traffic for that specific VLAN, and it doesn't need tagging because it only has one LAN. So if it has one LAN, why do I need to identify which one LAN it belongs to? And some computers, even though they can do trunking, only if you have like a server or something like that, you're required to do trunking. But for the most part, any computer, any laptop that has a wire connection, or any desktop, all the ports are configured as regular, for one native VLAN, and they'll connect to an access port. But all the others in the background that carries multiple networks on one line, on that line, on that connection, it will be trunk ports. And in this case, I guess they're trunking everything, even though they're using probably Cisco VTP, because that it would, from what I see here, it would mean that switch A is receiving also traffic for 1, 2, and 3. But at any moment that they need an access port on switch A for VLAN 3, they can just bring it up, assign access port on VLAN 3, and voila, there it goes. It received the traffic. I have no idea why they put this slide here, which refers to the example on figure 827 that's on the next one. So let's go there so we can explain this better. So this is more like I explained before. So between the router and switch C, you'll see that that trunking, it has all three subnets, 1, 2, and 3. And they're like separated by the VLAN tagging, whatever VLAN ID they put on that one. So it will be subnet 1, 2, and 3, the blue, red, and green. And the same thing happens between C and A and C and B. That's how you can traverse that traffic. And remember, a VLAN 1 on switch A and VLAN 1 on switch B, they assume to themselves that they are part of one same network. They don't need to go to a router. If VLAN 1 talks to VLAN 1, the switch is smart enough to send the traffic to C, and C will send it to A, and A will send it up to the client. Because there is no need to go to a gateway IP address, right? I'm not traversing two independent VLANs, two separate VLANs. It's the same VLAN, VLAN 1. So if I'm talking with my same VLAN, even though I'm across multiple switches, the trunking is there. So the trunk between BC and CA, VLAN 1 is trunking there, so it will make the connection, and it will appear for those two clients that they're connected right in one single room altogether. But like they can span multiple like buildings or floors. Here at the college, we kind of did that sometimes, that there were some VLANs that they were /24. We gave it out to multiple departments in different buildings, and became kind of messy because they were all over the place. So when there was a problem with that VLAN, then you got problems not in one location, but you got multiple locations with same VLAN, same network. They say 147.70, I don't know, 150. That's something, that's 0. And then you realize the 147.70, that 150 was configured in building 1 and building 3 and grounds all the other side of the campus. And there was a booth that was small, so we put it there too. And as far as those computers will be concerned, they're all in one LAN. They don't have to go to a router to talk to each other. But they were spanned across multiple switches, and that became messy too. So you got to be careful when you spend like that, to spend it on a organized way. So this is a nice graphic. It's one of those Cisco routers. That's like a RVC or something like that. There was one of, oh, it's right there. RV the 300 series. And I guess that port 1 is a trunking port, and it has VLAN 1, VLAN 2, VLAN 3. It has the subnet and the sub interface, because it has to have its own IP address. So each one will be allocated for that. And if that is a router, so it's able to do the trunking and probably be the gateway for those three networks. So common names for the VLANs, I mean, you'll hear this. The default VLAN is typically where it's pre-configured on the switch, and with not much configuration, or the standard configuration, that's your default what you get on that port. If it defaults to VLAN 1, then you will get that. That's the default VLAN. Normally, you don't use that. You don't want to use the default VLAN. You want to create your own VLANs and your own VLAN number, because you don't want that VLAN. VLAN 1 comes configured, the default VLAN comes configured all the switches that you buy. So you don't want that VLAN 1 to be spanning through your whole enterprise. So rule of thumb, disable VLAN, the default VLAN, VLAN 1, and don't use it. Also, there's what is called a native VLAN. Native VLAN is the one that's presented on the port and tagged. This is like an access port. So the access port is with no tagging. So it's what's called untagged port, untagged frames. And that is what is presented on a specific port or for a specific VLAN. It could be the native VLAN, could be 10 or 20, 30, whichever VLAN it is configured, but it's presented to the client as that. Then you can have a data VLAN, for email browsing, that, anything that you want to call, have in there. Management VLAN, we do have that. Is one VLAN is just for management. At the college, we use one specific one for every campus that is only used for managed devices. Then you have a voice VLAN, or just for your voice traffic, the voice over IP. A private VLAN for something that, it has its own partitions. It's also separated, which it could be either an isolated or like a community VLAN, something they use for like a specific lab that is isolated. So you can have it like that. But this is some of the VLANs that you normally would have, but you can have your wireless VLAN too, and any other VLAN that you can have. but it's just a way to name them and separate the traffic, because this way now the management traffic is not mixed together with the voice or the data or your native VLAN, for the user. So like in our case, we have that, the management VLAN is like that, and then we put a restriction at the gateway because it's a separate VLAN. It has its own separate gateway. So we put a restriction, said, okay, to cross this gateway, you have to come from the data VLAN. So this is the data VLAN I have configured for my service, stuff like that, and those are the only ones that can actually get into the management and access the switches. So somebody on the voice or on the native VLAN, or well, the private will separate, but anybody on the native VLAN or the voice VLAN cannot talk to the management, because now the management VLAN is separated, has his own access controls that it has to come from only from the data VLAN. And there's so much that you can do there that it depends how you want to set up your network. But now you have control of how the traffic goes. And this is actually a good example where you have a switch with multiple VLANs, right? You have your VLAN 1 isolated, and the community VLAN 1 and community VLAN 2. So you see that even though each computer is connected directly to the switch, each port on that switch is configured for a specific VLAN. So the two computers on community LAN 2, they're able to talk to each other, but LAN 1 cannot talk to LAN 2, right? Because LAN 1 and LAN 2, they cannot talk directly. They have to go through the router, and that has to be configured the router. And then the isolated VLAN 1 is also a VLAN 1 that you have, but it's completely isolated. So that, I don't know what the example put in there, but it has no purpose there because you have a computer connected to a switch that doesn't talk to anything, but anyway, is there. And then you have a server that it has a port called a promiscuous port, that one is able to talk to all the others. That way, it's able to provide, a backup service or DHCP or any other things that you want to have into that private LAN for them to communicate. But by segmenting with the VLANs, now you can control. There's no gateway, so you're not able to communicate from one VLAN to another, from 1 to 2, or from the isolated is isolated. So, but you control the traffic like that. So to view your LANs, for the most part, even though this is a Cisco command, show LAN or show VLAN, that can be applied to some of the switches. Some of them mimic a little bit the Cisco command. Sometimes you have to show VLAN or show VLAN ID and the number, so you see which ports are being used by a specific VLAN. And there's an example on the next page. Let's go to it. And I'm laughing because this is the example for the book. It's like, yeah, there you go. That's where you can see your VLANs, but it's so hard to read that I'll show this in class, and I'll log in into a switch and I'll show you other VLANs, how they're shown and how you can identify which ports are allocated to specific VLANs, or if you want to show all the VLANs that are configured on the switch. But you can see that on the book that is a little bit more, bigger, better to see. Is on page 455. You can also have what is called dynamic VLAN assignment. For dynamic VLAN assignment requires a lot more configuration, a few more servers involved in that whole communication. You can be doing that with a radio server. That when the connection comes in with the client information, then of course it's going to have the MAC address or the location or the machine name. And with the machine name, you can see if it's a Kendall machine, a Wilson machine, a West Campus machine, whichever campus you're talking from, and of course your client information, because you had to log into the computer. So all the information is passed to the radio server, and based on that, you can have what's called a NAC, a network access control, that it can allocate the specific VLAN that you're supposed to be on. That is kind of tricky to do. You need the switch to be configured for that. You need the radio service to be configured for that, and your NAC, your network access control servers, also to do that. Cisco does it with Cisco ICE right now, and but even for ICE, it's a little tricky to get it to work because of the IP addresses. But phones do that and do it perfectly. Phones will actually come into the port and they'll come up, they will go to the DHCP, get an IP address on my data VLAN, and then the data VLAN connects you to the DHCP server, and the DHCP server can send you a whole bunch of information. There's a ton of information that you can relay from the DHCP server. Some of the information is the voice information. And I can tell a client that connects it to a specific port, and it goes, okay, you're like we do at the college is that if you're connected to a port on VLAN 30, your voice VLAN is VLAN 130, just to match it and make it easier. So when you connect to VLAN 30, they go to the DHCP. The DHCP gets an IP address and give you an IP address on the 30 network, 147.70.30, that's something. And in that DHCP header, there's information for your VLAN network and your VLAN ID. It says it's going to be not VLAN 30, but it's VLAN 130. So the phone gets the information. It goes, oh, okay. So let me reboot. And now he reboots with the port tag on VLAN 30, VLAN 130, because that's the voice VLAN, connects again to the port. It goes to that gateway, the 130 gateway. He gets the DHCP information, and now he gets all the configuration for the phone for VLAN 130 along with the IP address on 147.70.130. That's something. So now phone dynamically got the first reply on VLAN 30, but then he said, oops, I'm on the wrong VLAN. This is not the voice VLAN, so let me reboot now and connect to that one. And he dynamically moved itself to VLAN 130 based on the information given by the DHCP server or a radio server or any other a network access control application that you may have on your network. So you get some errors they can get on your VLANs. If you got the incorrect VLAN assignment, you'll be connected to the wrong VLAN, right? For example, if your computer gets connected to the voice VLAN don't have access to the internet. So you try to go to Google or something like that, and it doesn't work because you're on the wrong on a VLAN that has no access to the internet, or the incorrect port mode. Computers need to have an access port. If it's configured as a trunk port, it's not going to work. The computer has no mechanisms to understand trunking. So and if it's configured as an access port, then and the other side is trunk, it doesn't match. It will not work. You might be connected to an isolated VLAN, so you can cut off from the rest of the network. When you do NAC, the network access control, you can create that and force that if I connect a computer that I brought from home, my own personal computer connected to the Miami-Dade network, and then the network sees that, queries that machine, the MAC address, and the name of the machine and all that, and determines that machine, it is not a Miami-Dade asset and not a Miami-Dade computer, it can throw that into an isolated VLAN that you'll get a connection, you might get an IP address, but it takes you nowhere. Because I don't want that computer on my network, so I completely get it out. Or I can actually disable the port and say, you're not part of my network, you're going to be completely isolated. You can have also VLAN hopping, when that's more like an attacker that starts like thinking that it belongs to multiple VLANs, or start like going across VLANs just to find where is a network that has data or something that it can have. And the same thing they can do with the for this VLAN hopping is to do double tagging, that they will connect to a port with multiple tags. So if one doesn't work, they will try to see if the other one works and like that. But that's kind of difficult because, like I said, it's 4,000 tagging numbers that you can have. So you have to be very specific of what you're doing. On the switch spoofing, is also they're trying to spoof the switch, but that's usually when switches that are auto configured, that if I come in and I said, okay, I'm a phone and I need to connect to the phone network, so switch the port to the phone VLAN, and to force the switch to reconfigure itself to go to on another VLAN. And imagine if that's your server VLAN, but that doesn't really happen. That's why I don't like that VTP, the virtual trunking, because if I don't have a need to define my server VLAN on my switches, then I don't put it there, and there's no potential problem that someone connected to my server VLAN, because it's not on the switch. VTP would allow to do that, but if you configure only the VLANs that you need on that switch, and the server VLAN is not supposed to be there, then it's not going to be there and it's not going to get attacked. So you avoid those problems, but just limiting the switch ports to the VLANs that are required in that area. And the switch itself configured with only the VLANs that are needed. If it's not needed, take it out. You don't know how many times I've been on some switches at the college that I see them, and I see VLANs configured that have not even one port configured on that VLAN. I said, what is this VLAN doing here? It's not being used. It's not needed. Somebody put it for whatever reason, but it's not assigned to any port. So I deleted it. I go and delete that and clean it up. I make sure if someone needs it, they can put it back. It's simple to go and reconfigure that. Someone has access to the switches, can reconfigure it. But if it's there for no reason at all, me personally, I'll go in and remove it for security reasons, for traffic reasons, just to get everything cleaner, and to have things that don't need to be there, just take them out. Some of the securing the network is, like I said, don't use the default VLAN. Default VLAN is VLAN 1. All the switches come pre-configured to VLAN 1. The unmanaged switches, all the work is on VLAN 1. Don't use VLAN 1. If it's there, if some switches don't allow you to turn it off, to disable it, but even if it stays enabled, then don't assign any ports to VLAN 1. Then you can also change the native VLAN to something unused. At the college, we use what we call like an empty bucket. The empty bucket is VLAN 999. So we allocate VLAN 999 that has no gateway, no nothing, no configuration. It doesn't even exist. But we create VLAN 999, and if a port is not in use or anything, we configure that port to VLAN 999. So that way, someone plugs in there, can go anywhere. That's a security reason, to have the ports not disabled. They still enable, but on a VLAN that doesn't really take you anywhere. It goes to an empty bucket. If you have auto trunking, disable that on the switches. If you don't need to support multiple VLANs on those ports, just disable it, right? So you only trunk on the ports that actually need multiple VLANs. All the other ones, they leave it as access ports. Of course, the uplink, the one bringing the connection from another building, from another floor into this switch, it has to be trunk. But all the other ones doesn't have to have trunking, right? Here, like I said before, specify the VLANs are supported on each trunk. Don't put any VLANs, extra VLANs that doesn't need to be there. They don't need to be there because it's a security problem to have them, right? And then physically secure the door locks and restrict the network equipment. You don't want to have a closet with switches that are wide open to anybody to pass through and see them and connect or try to break into those switches. We have all the doors are secure with a fob key with the ID, and the my ID can open all of those closets. Other professors that can open to the classrooms, but not the telephone closet. They are completely secure for that. So only the people that have access to that, even if it has a key, then only the people that require the key are the ones that can get into those rooms, just to secure your equipment. That's the end of chapter 7. No, 8. I'm sorry. Yeah, module 8. So we'll go in class a little bit more over this. This is something that is better to see it, not just like on a PowerPoint, because it's very, it's extensive. It's more visual too. It's better to see it to understand it better. But we'll cover more of this in class. And also refer to the book and the extra videos that I put on Blackboard, so you can get a little bit more information on how the VLANs and the subnets are configured and things like that. Okay, thank you very much.